Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the Beckmann rearrangement reaction and different example based on Beckmann rearrangement reaction. What are the starting material and what are the common reagent used for Beckmann rearrangement reaction, and what is the specialty where it is used in Beckmann rearrangement reaction that we have seen. So that type of the reaction and where it is used, how nylon 66 can be prepared by using as a Beckmann rearrangement reaction. One general reaction we discuss regarding that Beckmann rearrangement reaction. Let us talk about that Beckmann rearrangement reaction. For example, suppose let us consider here, suppose we have a starting material is this one. As we know that everybody knows that the structure of this organic compound, name of this compound is a cyclohexanone, right? This is the name of the compound which is written on the blackboard when it is treated with the hydroxylamine NH2 in presence NH. This is the name of this reagent known as hydroxylamine. This is known as a hydroxylamine, right? This is ammonia derivative. It is a reagent generally used for the preparation of ammonia, preparation of derivatives. So this is a compound ketone, cyclic ketone, which is cyclohexanone. What you are going to get over here, the oxygen from that from this cyclohexanone and hydrogen, two hydrogen molecule from this reagent, addition elimination reaction occurs and the resulting compound is obtained is this one, double bond. This is a regio selective type of the reaction, means at a specific region there is a formation of carbon nitrogen atom takes place, and when this compound is formed, this compound this product is known as oxime derivative. This is oxime derivatives which we have obtained over here. Now when it is treated with acidic medium H+, this is a Beckmann rearrangement reaction. Now Beckmann rearrangement reaction here takes place. So where what is going to happen here, this lone pair which is present on that hydroxyl group can pick up the proton from here, and we are going to get this type of the product, double bond N, then OH2. And as we know that, everyone knows that OH hydroxyl group is a bad leaving group. When catalytic amount of acid is used, that becomes that OH get protonated, and hence it becomes as a good leaving group, and that is a driving force here. What is going to happen here, the group which is anti to the hydroxyl group, that group is migrating from here to here, and we are going to get here the product like this N, then here generally double bond, then this type of the seven membered ring is formed here, positive charge on that compound, and now this molecule, this intermediate treated with water H2O, this water can attack on that carbocation, and the product you will get here. The compound is like this. The nitrogen atom I am writing as it is over here. Then here double bond OH is attacking like this, and rest of the carbon atom, they are remains as it is. Look at here, number of carbon atom 1, 2, 3, 4 and 5, and this one is the 6. Now this is enol type of the structure. They get at an equilibrium, the enol is get converted into as a keto form like this, and therefore you are going to get the compound which I am writing over here, nitrogen atom. This hydrogen atom is migrated from here on oxygen atom to the nitrogen atom, and here you are going to get the product is like this here, C double bond O, and this is called as a what we can call it epsilon caprolactam. Epsilon caprolactam. And lactam, why lactam? TUM means that amide group in a cyclic form. That type of the cyclic compound are known as a lactam, and when this lactam, this is amide type peptide bond is formed over there, and when it is treated with the base, strong base, what is going to happen? This peptide bond like get cleaved, and the resulting compound is obtained like this over here, N terminal and the carbonyl here. Suppose here we can write C double bond O, then here this CH2. Look at here, how many CH2s are there? 1, 2, 3, 4 and 5. CH2 5 time, or what we can call it as a, yes, 5 type, and then N, H, and this remaining here you can write as a N number of this type of the repeating unit, that is a monomer. This is a 1 unit of monomer, that is a we got as a polymer, and this is known as a nylon. This is a structure of nylon, and as we know that this is a epsilon caprolactam, which is used as a starting material for the synthesis of nylon, and this is a nylon, and therefore so this is one of the industrial application which is we already seen this reaction, but this is an additional part we have discussed here, why it is caprolactam is useful, because the this caprolactam can be prepared by using the starting material like this, and which reaction who discovered this reaction? Beckmann rearrangement. Rearrangement reaction means what? A reaction in which the carbon skeleton or the functional group or both are modified is known as rearrangement reaction, and how this atom or the group rearranged, and finally we are getting how nylon can be synthesized industrially. So that is the application of that Beckmann rearrangement reaction. So now today what we are going to discuss, we are going to discuss about the remaining rearrangement reaction. What are those remaining rearrangement reaction? We are discussing one by one with their examples, as well as what are the essential or the what are the important point to remember regarding those rearrangement reactions. So let's discuss about the Beer-Villiger rearrangement reaction. Next one is the Beer-Villiger rearrangement reaction. Rearrangement reaction. Beer-Villiger rearrangement reaction, or sometimes it is also known as Beer-Villiger oxidation reactions. So this is one of the important rearrangement reaction as far as organic chemistry is concerned. And why this is important, what are the important point to remember regarding Beer-Villiger rearrangement reaction, or why it is referred as Beer-Villiger oxidation reaction, and what are the starting material and what are the product is obtained, why it is known as Beer-Villiger oxidation reaction. So here just remember the starting material used for this rearrangement reaction is a ketone. Generally ketone may be aliphatic ketone or the aromatic ketone, and these ketones when reacted or treated with or allowed to react with peracids or or peroxides. So what is happening there? There is a deficiency oxocation ions are formed, and means oxygen atom here is found electron deficient in nature, and there is a migration of alkyl group takes place, and the resulting compound obtained as a what we can call it as a sometime is a acid, or oftenly it gives the esters. Means you remember the conversion of ketone in presence of peracid preferentially gives an ester is known as Beer-Villiger rearrangement reaction or Beer-Villiger oxidation reaction. So these are the general point you should remember as per as Beer-Villiger rearrangement reaction. How the rearrangement or orientation of atom, how the systematically that carbon atom get oriented or arranged, so that we will see while discussing the mechanism. And as we know that mechanism means what? A detailed study of sequence of steps which are involved in the conversion of reactant into product is known as mechanism. And in terms of the organic chemistry, mechanism is nothing but as a language of organic chemistry, and once you know the language, you can express your thoughts or you can convey whatever you want to say, that the listener can understand you in a better way, in a simplified way. So that is the medium which we are using in organic chemistry. So to understand this type of the mechanisms are there. So now let us see how this reaction is useful in converting ketones to esters by means of peracids. And in this migration of a group from carbon to electron deficient oxygen, that is oxacations, takes place. The acid catalyzed reaction of ketones with hydroperoxide derivatives is known as the Beer-Villiger reaction, is also called as oxidation. In this, esters of lactones are cheap product from ketone as a starting material, and in this discrete oxidation is drawn as the intermediate, but it is more likely that the rearrangement is concerted reaction, as we know that the bond making and breaking taking place simultaneously. That type of the process is known as concerted process, which we have learned. SN2 reactions are concerted reaction. We have learned in a semester number 3 while studying the nucleophilic substitution reaction at aliphatic carbon. If you remember, if you recall those third semesters, chapter number 3, I think, then you come to know that about the concerted reactions. And added other, the per acid is added to the carbonyl group. The rearrangement may be facilitated by an intramolecular hydrogen bond. General reactions is generally shown over here. General reaction, we are talking about this one. General reaction. So as we know that R, then C double bond O, R1, R2, we can call it over here. Then when it is treated with the Z, O and H, this is what we can call it peroxide, right? Peroxide, this hydrogen peroxide, generally we know that HOOH. This type of the peroxides are used over there. So what is going to happen? Generally in presence of the H plus, these reactions are carried out or taking place. What you are going to get here? R, then C, O, then here we can write O, here you, this side you can write as a O, H, then here O, and this Zn, not Zn, here is a Z is another group which is over there, and there you can write R1, this is R2, then resonating structure we can show over here. Here H plus, loss of ZNO, H over there, means like this, and H from here. So you are going to get here R, C, then maybe as a here this forming double bond O, then O positive charge over, here is a R1 and R2. This R is migrating from here to here, and the resulting compound will be obtained. 1, 2, 3, 4, 5 bond is never seen over there. So here still this is not shown over there. Here you can show only as a O, and this is, now this is forming over there, and after that it is migrating from here to here. So the finally what you are going to hear, where Z is equal to, where Z is equal to maybe as a hydrogen, or you can take as a R group, or you can take as a RCO, acyl group, or you can take as a ARCO group, etc. These group you can take over there, and but rearrangement reaction will occur, and you get here R, C double bond O and R1. So this is R2. It is nothing but as an ester. As we know that ester having as a general formula R, C double bond O, R dash is known as a ester. Or in other way around, we can define esters, definition of the ester or the statement of ester in the organic compound having a general formula R, C double bond O, R dash is known as ester. So this is a general definition of that ester. Or here, when that migratory aptitude of various substituent groups is generally, here what is happening, migratory group means this, which group, whether the R1 is going to migrate or R2 is going to migrate, that is the main point of discussion over here. So migratory aptitude here, remember the migratory aptitude means which group is going to migrate preferentially. So there are different group, alkyl group, aryl group. So which group is going to migrate? So there is a migratory aptitude order here generally is a tertiary alkyl. Tertiary alkyl group is generally migrate better than secondary alkyl group. Then there will be what we can call it as a secondary alkyl as well as benzyl. These are having they are having approximately same migrating aptitude, and then again as a phenyl as we know that, and then as we know that the primary alkyl halide, then primary alkyl, and lastly the CH3 methyl groups are there. This is a migratory aptitude. Here tertiary alkyl group as we know that, this one, secondary alkyl group we know that, this one, and benzyl we know that, benzyl means what, pH and then CH2. Phenyl we know that this is a pH, and primary alkyl we know that the primary alkyl may be as a CH2, then CH3 like this, primary alkyl, and then this is a methyl group. These are the what we can call it as a migratory aptitude is very, very important as far as this Beer-Villiger oxidation reaction is concerned. Then alkyl stereo selective factor. Stereo selective factor, it is one of the main point to introduce here in a Beer-Villiger oxidation reaction. So stereo selective factor favor an anti-periplanar orientation of migrating group to the leaving group, and will control the rearrangement is some cases but mostly per acids with retention of configuration, and reaction is stereopacific reaction. If there is a chiral centers are there, and as we know that only one chiral centers are there, it can rotate the plane of polarization either left hand side or the right hand side. It may be R configuration or the S configuration. Suppose your starting material has a R configuration, when you carry out the reaction by using per acids, the resulting compound form as a chiral in nature, and the resulting configuration is retained. So your substrate has a R configuration, product must have a R configuration. Means these kind of the reaction are known as stereopacific reaction. Stereopacific means only those reactions are, only those products are obtained, expected desired products are obtained. So that type of the compound, that type of the reaction are known as stereopacific reaction. Understood this? What do you mean by the stereopacific reaction? Because these rearrangement reactions are controlled by the stereopacific. Your starting material has a R configuration, resulting compound final product must have a R configuration. If suppose your starting material has a S configuration, the resulting compound must have the S configuration, means your configuration is retained over there. Such kind of the chemical reaction are known as stereospecific reaction. Suppose an aldehyde are usually converted to carboxylic acid under the above condition. Suppose you have a starting material, this one, whatever general reaction we have seen over here. If you have a starting compound is this one. Which one? This one. Suppose your starting compound have a let us see here, I am showing one of the compound CHO, and I am joining the nitro group to that benzene ring or a benzene moiety. So this is known as a para-nitrobenzaldehyde, because this is a benzaldehyde is one of the what we can call it as a main functional group, and para is a second one, so you give the priority to second. So para nitrobenzaldehyde. So this is the name of this compound. When this compound treated with per acid, as we know that per acid means performic acid, per acetic acid, per benzoic acid, metachloroperbenzoic acid. These are the per acids name, and they gives here the product is like this. Here we are getting O2N. This functional group remains as it is, but here we are getting this type. What are the changes occur here? Look at here. Aldehyde group is get converted into carboxylic group here. So that the oxidation occur in presence of per acid, and generally per acids are like this. Suppose we have this one H C double bond O. Remember there are 3 oxygen atoms are there. This one is known as a performic acid. This is the name of that compound. Performic acid means per acid. Suppose if you take here instead of hydrogen, if you take as a methyl group C double bond O and H, then it is called as a peracetic acid. And if you take here instead of methyl group, you take there is a benzene group, then C double bond OH, it is called a perbenzoic acid. And if you connect, this is known as a metachloroperbenzoic acid, this one. Suppose you have at meta position chlorine atom, the same C double bond OOH is known as metachloroperbenzoic acid. This is a commercially available. M stand for at metachloroperbenzoic acid. This is a full form of that MCPBA, metachloroperbenzoic acid. So let me write over here. It is a metachloroperbenzoic acid, and in short it is called as a MCPBA, metachloroperbenzoic acid. So these are the per acids are more commonly used reagent or possible to avoid the product formation, and common per acids are perbenzoic acid, peracetic acid, metachloroperbenzoic acid, peroxy trifluoroacetic acid. Per means like this, CF3 3 C double bond O and OH. This is another one per trifluoroacetic acid. This one per oxy trifluoroacetic acetic acid. So these are the some of the reagent generally used to perform the beer vinegar oxidation reaction. Got it? Now let's us see the general mechanism with this per acids. How we can show that mechanism over here. Let's see the beer vinegar rearrangement reaction. General mechanism with per acid. General mechanism with per acids. That's the we are talking about over here. And generally we have a starting compound R C double bond O R dash, right? And now when it is treated with the per acids, so first of all these reaction are reversible reaction. H plus in acidic medium, it get protected, so R C double bond O H positive charge, then R dash. When the catalytic amount of the acid is used over here, the carbonyl oxygen atom get protonated, and in this case the carbonyl carbon is more electron deficient in nature, and therefore the nucleophile can attack over there, and we will get this type of, or you can write this one in this way also, R C OH positive charge over there, and there R dash. And now when we are treating this with per acid O C double bond O R, that is generally double dash we can call it over here. Now the lone pair which is present on that acid is going to attack on that carbocation, and so you may get here I am writing this one R C O H, then here O H O, then R double dash, and this is R dash already there. Now look, observe this structure carefully. What do you see? One of the oxygen atom has a 3 bond, and therefore I must put the positive charge on that oxygen atom. In the next one, what is going to happen? There is a loss of H plus. Proton is lost over there, and you are going to get R C O H, then R dash O, then O, and R double dash we can call it over here. And now again in a next step, what is going to happen? Again there is a acid. This hydroxy group get protonated over there like this. So you may get here R OH2 positive charge over there, R dash, then O and R double dash, right? Now what is going to happen here? The H plus, sorry, here is a H plus is lost, not protonated. H plus is lost over there. So here what is going to happen here? This bond is moving, forming as a double bond over there, and at the same time this R group is migrated from here to here, and this get U all. So you are going to get here R C double bond O, then O, then what we can call it as a R dash ester, and plus R O and H, that is alcohol is formed over there, and this compound is known as an ester. Ester is a general formula which we got over here. So this is a general reaction of this beer vinegar rearrangement reaction, or we can call it as a beer vinegar oxidation reaction. I think there are number of examples of there. So the example of beer vinegar oxidation reaction that we will see tomorrow's lecture. Let us stop today here. Thank you. Have a nice day.